Hello, this is your instructor, Richard Collins in ATM101 Weather and Climate of Alaska. Welcome to Wind and Weather, Unit 9. In this unit, I review how wind is generated in the atmosphere and the forces that generate the wind. I also present winds associated with different meteorological phenomena, such as jet streams, cyclones, and anticyclones, and different meteorological and geographic conditions, such as land and sea breezes, mountain and valley breezes. In this unit, we will review how pressure gradients arise from differential heating of the atmosphere, explore how pressure gradients generate wind, examine the effect of the Earth's rotation on the wind, examine the effect of surface friction on the wind, explore how the balance of forces determines the wind in jet streams, cyclones, and anticyclones, and explore how different winds are established in different geographic settings. This lecture supplements our textbook, Weather, A Concise Introduction by Gregory Hakim and Jerome Patou, with material from the textbook Meteorology Today by C. Donald Ahrens. Let's start with a simple model of the atmosphere, where the atmosphere is represented as a simple column of air. From the ideal gas law, we expect that when the column of air is heated, it expands, and when it is cooled, it contracts. If city 1 and 2 are at the same temperature, then the columns of air have the same height. The pressure at the half height level is equal, as it is due to the weight of the upper half of the column. When city 1 becomes colder and city 2 becomes warmer, then the column of air over city 1 contracts and the column of air over city 2 expands. Now there is less air above the column in column 1 and more air above the level in column 2. The pressure is greater in column 2 as there is more weight above that level. Thus, we now have a change in pressure with horizontal distance as we travel from city 1 to city 2. There is a net pressure pushing air from city 2 to city 1. This behavior is consistent with thermodynamics, where energy will move from a hotter object to a colder object. As air moves from column 2 to column 1 aloft, the amount of air over city 2 decreases and that over city 1 increases. The surface pressure at city 2 now is less than the surface pressure at city 1. There is now a surface pressure gradient that forces wind to blow from city 1 to city 2. Thus, we have a circulation cell, with a wind blowing from city 2 to city 1 aloft, descending over city 1, blowing from city 1 to city 2 at the surface, and rising over city 2. Formally, we have a pressure gradient force, or PGF, that pushes air from regions of high pressure to regions of low pressure. This picture captures the essentials of how wind is generated. Differential heating of the Earth creates horizontal differences in pressure that drive the horizontal winds. So due to variations in temperature, we have pressure differences in the horizontal at a given height. A given pressure level, for example 500 millibars or 500 hectopascal, will be at 5,000 meters or 500 decameters for a given standard temperature. This height will rise by a kilometer or so as the air is warmed and fall by a similar amount when the air is cooled. Following a given pressure yields a surface like the Earth's surface on a map that moves upward and downward in elevation, where in warmer regions we are at a higher elevation and in colder regions we are at a lower elevation. On these constant pressure surfaces, the pressure gradient force points downhill. This is why these surfaces are useful to meteorologists, as they reflect geographic maps and are intuitive. This behavior is a big deal for small aircraft. These planes have altimeters that use pressure measurements to determine their altitudes. The conversion from pressure to altitude is based on a standard atmosphere at a standard temperature. In a warmer atmosphere, the plane's altitude is actually higher, and in a colder atmosphere, it is actually lower. In very cold weather, the planes may accidentally hit hills, tall buildings, or the ground. This is why the Federal Aviation Administration suspends flights during extreme cold. These principles are clearly illustrated in nature in the formation of land and sea breezes. The sea breeze is the cool breeze from sea to land that forms in the afternoon in coastal regions and keeps beachgoers cool. The land breeze is the warm breeze from land to sea that forms at night. During the day, the land absorbs heat from the sun and warms up rapidly, while the sea warms more slowly. The slower heating of the seawater is due to the high heat capacity of water, the mixing of surface and deeper water, and the absorption of sunlight over a greater depth in the water. See the discussion of heat and energy transfer in Chapter 4. As the land warms, the pressure Surfaces above the land move upward. At a given altitude, there is now a higher pressure over land than sea, and a pressure gradient force is established aloft from land to sea. Air begins to move from the land to the sea. At the surface, low pressure now forms over land and higher pressure now forms over the sea. A return pressure gradient force is established from sea to land at the surface. And so a circulation cell is established with a sea breeze at the surface and a land breeze aloft. At night, the reverse occurs as the land cools faster than the sea. A surface breeze is established from land to sea. I leave it as an exercise to students to fill in the steps that lead to the formation of the land breeze, and you should think of this in terms of a possible exam question. Newton's laws of motion are at the core of classical physics. They explain how things move from small scales such as balls on a pool table to large scales such as moons around planets. The three laws can be summarized as follows. 1. A body will remain at rest or continue to move with constant speed and direction unless acted on by a force. 2. The acceleration of the body is proportional to the force. The force is equal to the product of the mass and the acceleration of the body, and this law is often stated as F equals ma. 3. If a first body exerts a force on a second body, that second body exerts an equal and opposite force on the first body. The first law was initially controversial in some circles, as the idea of invisible forces such as gravity acting on bodies through invisible means smacked of magic rather than rational science. However, if a ball rolling on a pool table slows down, then a force, in this case friction, must be acting on it. Similarly, if a moon changes its direction to stay in orbit around a planet, then a force must be acting on it. The second law explains the inertia of bodies. For a given force, bodies of a larger mass change their motion by a smaller amount than bodies with a smaller mass. This is one way that exoplanets can be detected. The gravitational force between the Sun and the planet results in a small wobble in the Sun that can be detected from far away. The third law explains why the Earth keeps its moon in orbit, and the moon gives rise to the tides on Earth. A nice investigation of the third law is to stand on a weighing scales in an elevator and explain why your weight increases and decreases as you go up and down in the elevator. The pressure gradient force is just one of four forces that are acting in the atmosphere and determine the character of weather systems. The other three are the centripetal force that keeps air circulating around low and high pressure centers, the friction force between moving air and the surface of the Earth that slows the air down, and the Coriolis force that is used to compensate for the fact that our weather is occurring on a rotating planet and not, as Mr. Newton would prefer, on a stationary body in space. The action of all these forces is present in a hurricane, with its rotating winds that spiral inward to a central low pressure. The image of Hurricane Dorian with its perfectly circular eye is a perfect example. This Category 5 hurricane is the greatest natural disaster to hit the Bahamas. The Bahamas are the islands that lie to the east of Florida. The capital, Nassau, is 300 kilometers from Miami. The hurricane had a death toll of 84, with 245 people missing. While it is not a perfect explanation, the movement of a ball thrown across a merry-go-round gives a conceptual explanation of the Coriolis force. If the merry-go-round is stopped, then the ball travels in a straight line across the merry-go-round. The pitcher, catcher on the merry-go-round and an observer overhead see the same motion. However, if the merry-go-round is spinning, then the ball follows a straight line and misses the catcher. If the overhead observer spins with the merry-go-round, pitcher, and catcher appear fixed, and the ball appears to veer to the right when the merry-go-round spins counterclockwise. Thus, there appears to be a force that moves the ball relative to the rotating merry-go-round. On a rotating Earth, a plane traveling appears to be deflected as the Earth rotates underneath it. This deflection increases with latitude. There is no deflection at the equator and a maximum deflection at the pole. The Coriolis force is zero at the equator and increases with latitude. It is strongest at the poles. The Coriolis force also increases as the speed of the object increases. The force is zero on a stationary body and increases as the body speeds up. The Coriolis force deflects objects to the right of their path in the northern hemisphere and to the left of their path in the southern hemisphere. The balance between the Coriolis force and the pressure gradient force explains the movement of air between areas of high and low pressure. This balance defines the geostrophic wind. We can ignore friction if we're considering altitudes a kilometer or so above the Earth. Consider a pressure gradient characterized by the height contours on a 900 hectopascal map. The 900 hectopascal level is typically found 1,000 meters or 100 decameters above the surface, being higher in warmer air and lower in colder air. The pressure surface slopes downward from the warmer air and the pressure gradient force points downhill. In this example, in the northern hemisphere, we can think of the pressure gradient force pointing north and the isobars and height contours running east-west. An air parcel at rest is initially accelerated by the pressure gradient force from the higher pressure to the lower pressure. As it accelerates, the Coriolis force increases and deflects the parcel to the right. As the parcel speeds up, the Coriolis force increases and the parcel is further deflected to the right. As the air parcel turns to the right, the Coriolis force rotates from being at right angles to the pressure gradient force to being opposite to the pressure gradient force. At this point, the parcel is moving at right angles to both forces and is no longer being accelerated. The pressure gradient force and Coriolis force are now equal and opposite, and the air is moving steadily at constant speed and direction. These winds are called geostrophic or earth turning. They are generated by the action of the pressure gradient force and the turning of the earth. The math shows typical numbers for a change of pressure of 8 hectopascals, or 8 millibars, or 800 pascal, over a distance of 200 kilometers, or 200,000 meters. The pressure gradient is 0.004 pascal per meter, or 4 by 10 to the minus 3 pascal per meter. Pressure is force per unit area, so 1 pascal is 1 newton per meter squared. A pressure gradient has units of force per unit volume, or newtons per meter cubed. What happens if the north-south pressure gradient increases as the wind blows from west to east? As the pressure gradient increases, the contours of pressure and height move closer together. The pressure surfaces become steeper, and so we expect the winds to increase. This is analogous to a river, where the speed of the river increases as the river narrows and the banks of the river move closer together. Let's consider the acceleration of air on the 900 hectopascal surface as the pressure gradient increases. The pressure gradient force is a force per unit volume. Density is mass per unit volume. Using Newton's second law, the force per unit volume equals the product of the density and the acceleration. Knowing the density, we can calculate the acceleration at each point along the east-west path. The acceleration numbers are hard to interpret by themselves, but if we consider the force acting for 1 hour, or 3,600 seconds, we can determine the wind speed after 1 hour by multiplying the acceleration by 3,600. We see that as the contours narrow from 200 kilometers to 68 kilometers, the wind speed increases from 13 meters per second, or 47 kilometers per hour, to 38 meters per 137 kilometers per hour. We can also calculate the geostrophic winds directly from the balance between the pressure gradient force and the Coriolis force. Equating these two forces, or more correctly forces per unit volume, we can solve for the wind speed V. We look at the wind speed at 40 degrees north, the canonical mid-latitude, and at 65 degrees north, the latitude of Fairbanks that we know and love. From the math, we see that the mid-latitude balanced winds are larger than those due to the simple acceleration over 1 hour. We also see the effect of latitude through the increase in the Coriolis force with latitude. It takes a smaller wind to balance the same pressure gradient force at 65 degrees north than it does at 45 degrees north. This means, in Arctic storms, we can have near hurricane-size pressure gradients that fortunately yield less than hurricane-scale winds. We can also calculate the geostrophic wind for curved flows, where again the wind flows parallel to the height and pressure contours. On the 500 hectopascal map, the pressure gradient force points downhill. A ridge, where the contours rise poleward, has higher pressure on the equatorward side, pushing the contours poleward. The pressure gradient force points poleward, the Coriolis force points equatorward, and the forces are equal in magnitude. A trough, where the contours dip equatorward, has a lower pressure on the poleward side, pushing the contours equatorward. The pressure gradient force points equatorward, the Coriolis force points poleward, and the forces, again, are equal in magnitude. In solving for geostrophic winds, there are 4 steps. We first identify the direction of the pressure gradient force, the downhill, so to speak. We then note that the Coriolis force is equal and opposite to the pressure gradient force. The Coriolis force is to the right of the wind, and we can then draw the wind. And the winds increase when contours are closer and decrease when they are further apart. Winds that blow in a closed loop, where the air parcels orbit at a local minimum or low, are a maximum or high in pressure, are called gradient winds. For an object to follow a circular orbit, there must be a centripetal force that tugs at the parcel to stay in orbit. Without that centripetal force, the parcel would fly off the orbit at a tangent, following Newton's first law. Around a high, the pressure gradient force pushes outwards, while the Coriolis force turns the air parcel to the right. This eventually leads to a balance where there are clockwise winds around the central high. Finally, the parcels achieve a speed such that the inward Coriolis force exceeds the pressure gradient force, and that margin is the inward centripetal force. Around a low, the pressure gradient force pushes inward, while the Coriolis force turns the air parcels again to the right. This eventually yields a counterclockwise wind around the central low. Finally, the parcels achieve a speed such that the outward Coriolis force is less than the pressure gradient force by a margin, and that margin is the inward centripetal force. For a given pressure gradient force, the Coriolis force is higher in a high than a low, and so the wind speeds are higher in the high. In reality, the pressure gradient forces of lows exceed those of highs. Highs are associated with lower pressure gradient forces and weaker winds. Lows are storms, associated with higher pressure gradient forces and stronger winds. Adding the centripetal force to the flow between open isobars revealed something very important. At A, the peak of the ridge, the Coriolis force is greater than the pressure gradient force and the wind is stronger. Between the ridge and the trough at B, there is no curvature to the trajectory, therefore the centripetal force is 0 and the Coriolis force is equal to the pressure gradient force. The wind is now weaker than it was at A. At C, the bottom of the trough, the Coriolis force is less than the pressure gradient force and the wind is weaker again. Thus, the air piles up between the ridge and the trough like traffic slowing on a highway. Where does the air go? If it just piles up, it would create a back pressure and stop the wind. The air does not pile up, but moves vertically, which has huge consequences for weather. Returning to the surface, we now need to consider friction. Friction is the contact force that slows motion. For a body at rest, there is no frictional force, and the frictional force increases as the body speeds up. For a given pressure gradient force, the wind is now weaker than in the case without friction, such as we had aloft. As a result, the Coriolis force is reduced and does not exactly balance the pressure gradient force. The parcel now drifts toward the lower height rather than traveling parallel to it. For land, the wind blows at an angle of 30 to 45 degrees to the isobars. Over water, the friction is reduced, and the wind blows at an angle of about 15 to 30 degrees to the isobars. This behavior is evident in the surface weather map, where the wind barbs turn inward toward the low and outward from the high. The behavior is even better shown using streamlines. Streamlines are lines that give a snapshot of the velocity, speed, and direction at an instant of time. The streamlines clearly show flow outward from the high and inward toward the low. We have seen that at a surface, wind converges at a low and diverges from a high. If the motion was just 2D, the low would accumulate air and there would be a back pressure that would stop the motion. Conversely, the high would be evacuated and the outward motion would cease. 3D saves the day. Air rises at a low and prevents pileup. Conversely, air falls at a high and resupplies the evacuated air. This defines the weather of highs and lows. Descending air warms due to adiabatic compression. Thus, condensation does not occur and clouds do not form. Highs are associated with clear skies. Conversely, rising air cools due to adiabatic expansion. Thus, condensation can occur and clouds can form and precipitation can fall. Lows are associated with cloudy skies and rainy or snowy weather. This behavior connects to our ridges and troughs aloft in the jet stream. As air travels from a ridge to a trough, it slows down, and instead of piling up, it can fall. The falling air can resupply a surface high. Traveling from the trough to the ridge, the air speeds up, and the air can be resupplied by the air rising from the surface low. Thus, the structure of ridges and troughs in the jet stream supports the surface highs and lows. This is very important when we discuss the development of storms. We can analyze the weather in mountains and valleys in a similar way that we analyzed coastal weather and the land and sea breezes. During the day, the mountain walls heat faster than the air and creates a buoyant layer of air at the surface. The warmer air flows upslope. This is called a valley breeze. Meanwhile, colder air sinks into the valley. A circulation cell is established. Cumulus clouds can form over the mountain tops with showers. At night, the mountainsides cool and form a drainage flow into the valley. Cold air sinks into the valley floor, and fog often forms in the cold valleys. The flow can support the development of inversions, trapping of admissions, and reduction of air quality. Drainage flows in the Tanana Valley contribute to the cold conditions in Fairbanks in the winter and amplify the cold conditions on the valley floor. Katabatic winds form in mountainous regions. The word katabatic comes from the Greek katabatos, meaning descending. These winds are often associated with ice plateaus and glaciers. Air cools over the ice surfaces and becomes very dense with a local dome of high pressure. The air is then forced through gaps and valleys in the mountains and descends rapidly. While the descending air warms due to adiabatic compression, it remains colder than the local air and appears as a strong cold wind. Katabatic winds are infamous on the coast of Antarctica. Studies on the La Perouse Glacier in Alaska's Glacier Bay National Park show that katabatic wind and valley breezes can amplify climate change. Katabatic winds, when the glacier had advanced, reinforced periods of cold climate. Valley breezes, when the glacier had retreated, reinforced periods of warm climate. These studies have been based on old-growth conifers growing next to the glacier and support studies of how forest responds to rapid climate change. Finally, our summary and takeaways from Unit 9. 1. Variations in temperature due to differential heating and cooling yield variations in pressure. 2. Variations in pressure yield a pressure gradient force that drives horizontal winds. The pressure gradient force drives winds that blow from high to low pressure. 3. The land and sea breezes arise from the differential heating and cooling of the land and sea. 4. The Coriolis force is an apparent force due to the rotation of the Earth that causes winds to turn to the right in the northern hemisphere and to the left in the southern hemisphere. The balance between the pressure gradient force and the Coriolis force gives rise to the geostrophic or earth-turning winds. 6. Cyclones and anticyclones require a centripetal force that arises from the imbalance of the pressure gradient force and Coriolis force and gives rise to the gradient wind. 7. In jet streams, the gradient wind at ridges and troughs give rise to variations in wind speed along the jet stream. 8. In cyclones and anticyclones, the balance of pressure gradient force, Coriolis force, and centrifugal force gives rise to the circulating winds that are clockwise around a high and anti-clockwise around a low in the northern hemisphere. 9. Surface friction results in convergence at a low and divergence at a high. That results in rising air at a low and falling air at a high. This yields stormy weather at lows and calm weather at highs.